So just to gauge, how many of you have worked with microcontrollers before? And so I'll include like Arduinos, Espressif chips, like ESP8266s or ESP32s. Yeah, you can just put your hand up. Just want to get an idea of what everyone's experience level is. Okay, so, okay, that's good.
Lower your hand if it's Arduino.
Yeah, I was gonna say exactly that. If it's just Arduino, put your hand down because Arduino simplifies a lot of things. So we're gonna dive deep into what Arduino hides from you. Okay, cool. That's a good gauge on what we're looking at. Sorry, I just want to keep the chat open here. Cool. Okay, so we're gonna start with just an introduction to microcontrollers. What they are, what's special about a microcontroller. And then we'll talk a little bit about the architecture of a microcontroller, so what's actually going on inside. And then we'll get into some of the development tools that you'll be using that you may or may not have used before that are specific to you in interfacing with a microcontroller. And finally, we'll open it up for questions. Okay, so introduction. So what is a microcontroller? If you want a formal definition, it's a small-scale computing system with an integrated CPU, memory, and input-output peripherals, typically used in embedded systems. So essentially what it is it's just a compact chip that has everything you need to run a computing system all in one. And yeah, you can ask questions whenever. Just jump in. You can unmute and ask a question or send it in the chat, whatever works best for you. So some examples of microcontrollers. So on Arduino boards, most of them, they have this AT-Mega microcontroller. For AliaSat, we've got the TMS-570. If you've ever used one of these Espressif boards, they have a microcontroller in them. I think it's actually got the same name, the Espressif, like the ESP8266 is the name of the microcontroller. And then this is just a random one that I happen to be using recently, so I added it to the list, the EFR32 from Silicon Labs. So microcontrollers are unique in that they have some extra design constraints. This includes limited resources. So they generally don't have a lot of RAM. We're talking like less than a megabyte often. And they often also don't have a lot of non-volatile memory. So memory that is persistent even when the device loses power. So for example, flash memory. So our AliaSat microcontroller has I think 1.25 megabytes of built-in flash. So that's really not a ton of space. Relative to like 10, 20 years ago, that's tons and tons of space. But compared to your desktop computer, which has like, I don't know, 256 gigs of storage, that's pretty much nothing. Microcontrollers also have often, but not necessarily always, real-time computing requirements. So what real-time means is they are running tasks that have to complete their job by a certain deadline. And this is to make sure that the system is deterministic. So you can be confident that this task will finish at this time, this will finish at this time, and the system won't start lagging behind. And this is often really important in safety critical situations. So any controllers inside a car will pretty much always be real time, or on a rocket, or on a satellite, where satellite's not necessarily human safety critical, but something goes wrong with your satellite, then it's most likely going to be unrecoverable if it starts behaving non-deterministically. Microcontrollers also have a little bit more complex debugging interfaces than you might be used to on desktop machines. So it's usually pretty easy to debug a desktop program. You just attach your debugger to the running program. And it's nice and straightforward because your debugger and your program are running on the same hardware. But for a microcontroller, your development environment is on your computer, but your code is actually running on the microcontroller. So you need a bit more of an elaborate setup to actually debug that code. And I'll talk a little bit about what that looks like at the end of this module. So given that that's what a microcontroller is, let's look at what's on the inside. So this is the architecture of a standard microcontroller. It's really not too complicated. There's only a few components here. So first off, there's RAM. Every computer has RAM. I'm sure you're familiar with that. It's the memory that gets erased every time the chip is reset. So it stores all your kind of temporary information while your program is executing. Then there's flash memory, and so that's non-volatile. So it's preserved across resets and power cycles. And that typically is where you store your compiled code. So that's where your code actually lives. And you might keep data there that needs to be saved for future use. Then there's I/O peripherals. So these are the modules in the microcontroller that let it communicate and interface with external hardware. So GPIO pins, UART, SPI, I2C, any of those are all I/O peripherals because they let your microcontroller communicate with another device or just communicate with, basically interact with external circuits. Another example is ADC, so that's an analog or an analog to digital converter peripheral. So it can take an analog signal in and convert it to a digital value that the CPU can use. Then there's the system bus. So this is what allows the CPU to communicate with all these three other components: the RAM, the flash, and the I/O peripherals. Generally, so you've probably heard of like a 32-bit computer or a 64-bit computer. That is referring to the word size of the computer architecture. And so that in a microcontroller generally maps to the size of this, the address field for this bus. So basically determines how much memory you can address through the system bus. So I'll go into a little more detail on that in a couple slides. And then there's the CPU. So this is what actually executes your code. It controls the I/O peripherals. It does all the actual stuff. So for the TMS 570, so the TMS 570 refers to this whole thing, which is the microcontroller. And then the CPU inside is an ARM Cortex R4F CPU. So ARM is a pretty prolific CPU manufacturer. Their Cortex R line is used in lots of microcontrollers. This F just means it has floating point support, so it can do calculations on floating points. So looking here, the CPU needs to know how to talk to each of these modules. And the way it does that is they're all memory mapped. So what that means is there's an address space. And so this address space, it's the size of it is determined by the word size of your architecture. So for 32-bit, the max value of a 32-bit integer is about 4 billion. So you've got 4 gigabytes of address space. Hold on one second. So the RAM and flash memory are accessed at certain address offsets. So if you've got 1 megabyte of flash memory, that might occupy the very bottom addresses of your address space. And then there might be some reserved addresses in the middle. And then there's your RAM, and then maybe some more reserved addresses, and then your peripherals. This is a typical layout. So usually the flash memory is at the very starting addresses, and the peripherals are at the highest addresses. And so, yeah, so the memory map, so this is something that's going to be in the reference manual for your microcontroller. It'll tell you where, like which addresses correspond to which parts of the microcontroller. And yeah, so let's talk a little bit about how programming a microcontroller works. So you compile your code, it becomes machine code, and then we'll talk more about the compilation process. There's a question here. So what are the reserved addresses usually for? They're usually, like, they could be reserved for a future iteration of the chip where they maybe expand the size of different memories. Or they could just be a way to create some separation between different sections of the address space. But essentially any memory that's reserved, you just don't touch if it's on your microcontroller. Does that make sense? Does that answer the question? Perfect. Okay. So yeah, so programming a microcontroller. So you compile the code. Julian's actually going to talk about the compilation process in quite some detail a little bit later today. And then once your code is compiled, you write it to the flash memory. And this typically starts at address 0, like we showed here. So you upload your code into this section of the address space. And then when you power the microcontroller, the CPU starts by executing the instruction at its reset vector. So the reset vector is essentially the reset value of the program counter. And the program counter is the address of the instruction currently executing. So typically this is just 0. It's nice and easy to remember, very logical. You can change it though, and like some microcontrollers have it configurable. But let's assume it's 0 for now. So what that means is the CPU is going to start by looking at address 0, so the very beginning of your flash memory where you uploaded your code, and it'll execute the instruction there. So that will be the first instruction of your code. So that works out perfectly. And then the CPU will just start executing instructions either just in order, just by incrementing the program counter, or it'll branch, or depending on what your code actually does. And so on a microcontroller, your program doesn't exit, the CPU just keeps executing. So generally, there's an infinite loop somewhere in your program to keep it from escaping your flash memory space if it just keeps executing down the address space. Okay, I'll pause here for a sec. Does that process make sense? How a microcontroller is programmed and how the CPU executes its instructions? Okay, looks like we've got no questions, so we'll keep going. So if we dig a little deeper into this flash memory section, we can actually divide it up into a couple different parts. So typically, these different sections are called partitions. And typically you'll have at the lowest address, a bootloader partition, and then you might have multiple application images. So an image just means the compiled program. So the bootloader starts at the reset vector, for example, 0, because this is what you want the first code to run to be. And usually it's fairly simple code that's low risk, not going to fail. And it has kind of straightforward jobs like check that nothing has gotten corrupted in the application image areas. So there might be like a checksum of the application image stored alongside it. And so the bootloader can just check that, okay, nothing's gotten corrupted. The application image is good to go. And then it'll have a jump instruction to jump to the start of the application image. The bootloader can also enable you to do firmware updates. So the bootloader could have some code that lets it receive a new firmware image, like a new application image, either through a UART connection, a SPI connection, or whatever have you. And then it'll receive this image and write it to flash, overwriting one of these images. And then it'll check that there's no corruption, and then it'll jump to the new image. You can also have a bootloader update itself, but that gets complicated. And often if you're trying to minimize risk, you'll have a bootloader that is non-updatable. Some microcontrollers also shipped with a bootloader pre-programmed in. So most of these Arduino boards that you might have worked with have a bootloader already programmed in. And that bootloader can receive firmware images over that USB or UART connection. And so that's how you can upload code just by sending it over a USB cable. Then the bootloader writes it to flash and knows how to jump to it to start executing. So each app image could be a different program. It could be the older version in app image 1 and the newer version in app image 2, like after an update. You could just have one slot. It's entirely up to you how you structure your flash memory. You can, but yeah, so it's however you want it to be for your particular application. In the case of Eliasat, the way we've set it up is so there's a bootloader and then there's an application image on the internal flash. There's just one, and then on external flash, so we have like an external flash storage chip. We have some additional slots for application images that need to that are going to be updated onto the internal flash, and just a backup image if something goes wrong with the one in internal flash. So yeah, it's very customizable to the app, to the particular use case. Typically, you don't actually have multiple programs on a microcontroller. Like an embedded system is characterized by the fact that it has one purpose. So generally, there's one program, and these are just usually other app images or just different versions of that during updates. Okay, so let's talk a little bit about peripherals now that we've covered kind of the memory parts. So we'll jump back here for a sec. So peripherals is typically this highest address space. And inside here, it's divided into a bunch of subsections. So that could look something like this. So like from this address to this address is this peripheral. The HTU is a timer, I think. The hets are timers. This is an analog to digital converter. This is the GPIO module. This is I2C. So the peripheral address space is divided for each module that the microcontroller has for each peripheral. And the way you can control these peripherals is then just by, you can declare a pointer to the address you want to manipulate and then just write to it. Because that's the advantage of having memory mapped IO, is your peripheral registers are just part of the memory space your program can access. So in this example, I declared a pointer to what FFF7BC0, so the GIO module. And then this doesn't actually do anything useful. It's just an example. You can write to that register, whatever might be there, or you can read from it. We're going to do an actual interactive lab where we get you to write some code that writes to GIO registers and turns pins on and off to blink an LED. So we'll get to that in a couple sections. But yeah, so as an example of like one of the registers in the GIO section of that memory map is the data output register. So there's some of the bits control the output signal on the particular pins. So if you write like a 0 or a 1 to one of these bits, it'll set the corresponding pin to high or low. And then so these reserved pins, like I said before, with reserved things, you generally just don't use them. It has a defined behavior here. If you try to read it, it always returns 0. And if you try to write to it, it doesn't do anything. So that's peripherals. This is a slightly more advanced topic, direct memory access. So this is a way that you can transfer data between different regions of the memory map without the CPU being involved. So usually the CPU is what controls the system bus, and it controls the system bus to tell it where to move memory or where to move data between different memory regions. If, however, you need to move like a large chunk of data from a peripheral into your RAM or a peripheral into your flash, you don't want to be consuming the CPU just to move data from one spot to another spot. So lots of microcontrollers have support for direct memory access, or DMA. And what this essentially lets you do is, instead of the CPU controlling the system bus, the DMA controller controls the system bus. So it can instruct the system bus to move some data from the IO to the RAM without the CPU having to do anything. And what it'll do is it'll strategically do this when the CPU is, I don't know, doing some math that doesn't require accessing memory, or doing operations that don't use the system bus. And so that way it improves the efficiency of your CPU use, because this can slip in between CPU instructions. So it's great for moving large quantities of data between different memory regions. So that's a lot about the internals of a microcontroller. Let's take a little bit of a look at getting towards the kind of external parts of the microcontroller. So your microcontroller comes in a package. It's got a bunch of pins, but unfortunately, there's a finite number of pins. And usually it's a much smaller number of pins than the number of internal signals coming from all the peripherals and everything. So the way this is handled is usually the pins are multiplexed. So there might be 3 or more than 3 signals going to a single pin. And then there's some hardware register that decides which signal is actually connected to the pin. So you can see here, kind of illustrated, each pin has a multiplexer on the inside. And so this is sometimes called a pin mux. So for example, for the TMS 570, pretty much every pin is multiplexed to a bunch of different signals, and there's a configuration tool you can use to decide which signals actually get connected. And so this is how we deal with the problem of not having enough pins. So these pins can have different hardware configurations. So if a pin is configured as an input, and this is mostly relevant for general purpose input-output pins, GPIOs, but it can apply to other things like pins used for certain communication protocols, etc. So if a pin is configured as an input, it could be configured with a pull-up. So it could have a resistor to VCC, or I realized I have VDD in the diagram. So that means if the pin itself is not connected, then it won't, it will read a logic high level. Alternatively, you could have a pin pull down internally. So if the pin is not connected, it'll read a logic low level. Or there could be no pull, in which case, if the pin's not connected, then this voltage will be floating. So it could be somewhere in between high or low. And then when it's processed by the input buffer, it could be switching between high and low. So this is generally a situation you want to avoid. So you want to either use these internal pull-ups on inputs, or you want to make sure you're external to the microcontroller. You're either always driving high or low, or it's pulled high or low. So you don't want to have floating pin voltages usually if you're going to actually be reading that pin. If you're just not using it, then it's generally fine. So on the flip side, if your pin is configured as an output, there's 2 different types of outputs. So one of them is called a push-pull output. So the internal structure looks like this. This is a standard CMOS structure because there's a PMOS transistor and an NMOS transistor. And so complementary, CMOS stands for complementary metal oxide. Yeah, so floating pins can also be extra dangerous in space because you've got this ionizing radiation that can generate a signal on those pins when you're not expecting it. So yeah, in general, don't float pins if you're going to actually use them. So on the, back to the output side. So this push-pull configuration, because it's got a transistor up here and a transistor down here, it can either drive the signal high to like connect it to VDD, or it can pull the signal low, connecting it to ground. So that's pushing or pulling. An alternative is called an open drain configuration. And so this is the drain of the NMOS transistor. And so this is called open drain because in this configuration, there's nothing connected there. And so in this configuration, the microcontroller can only pull the signal low. It can't actually connect it to VDD, so it can't push it high. What it can do is it can not pull it low, in which case the pin is in what's called a high impedance state or a high Z state. And what that means is it's a high impedance looking into here because it's not connected to anything. And so this would be floating unless you have an external pull-up. So generally, if you're using a pin in this open drain configuration, you'll have an external pull-up so that when it's not connected to low, so when it's not being pulled low, it's being pulled high by the pull-up, so there's still a well-defined state. And so these are useful if you're going to connect multiple GPIOs together as outputs, because what you don't want to do is you don't want to have one GPIO driving high, the other one pulling low, and now you've got just a short between power and ground. So you never want to have that. This way, if you have multiple GPIOs, none of them can actually drive high, so you can't get that short scenario. You can either be pulling low or just letting the line be pulled high by this resistor, or maybe be pulled low by a different controller. So this is specifically like the most common use case I can think of is I2C connections. They use open drain outputs because there's lots of devices on the same line. And so they can either pull low or let the resistor pull it high. Does that make sense to everyone? These pin configurations? Are there any questions about that? Okay, I will keep it going then. So just kind of slightly unrelated, but another topic. Oh, we got a question from Kim. So open drain configurations are useful if the outputs are connected on the same line. Yes, exactly. So if I've got multiple devices, like multiple pins connected to the same line, and they're both or they're all outputs, then you'll generally want open drain so that you don't have one driving high, one driving low, and you don't get and you get a short. Okay, so Watchdogs. So this is just a common thing you'll encounter when using microcontrollers. So I figured I'd include it in this slide deck. So there's two types of watchdogs. The traditional watchdog is a hardware watchdog. So it's basically just a timer. And when that timer expires, it resets the CPU. That's called the watchdog biting. So to stop that from happening, the firmware has to periodically reset the timer. And that's called petting the watchdog, or if you're a little meaner, it's called kicking the watchdog. We're going to go with petting here. I think actually in the code base, they sometimes call it tickling the watchdog. Anyway. So the purpose of this is if the firmware freezes or hangs, then it won't be able to pet the watchdog and the timer will expire, and then it'll reset the CPU, so the watchdog will bite. And so this is how you can escape from a hang situation. Often, we also have a software watchdog. So it's kind of like a multi-stage watchdog. So in your software or your firmware, you might have multiple tasks doing different things, and then you'll have a watchdog task. And so these tasks check in with the watchdog task, and then the watchdog task checks in with the hardware watchdog. So it's just a way to kind of multi-stage your watchdogging. Any questions about watchdogs? Okay. We'll keep going then. So now we're going to talk about dev tools. So this is going to be very useful for anyone starting their firmware development on like actual hardware or even on the dev kits. So to start off, an integrated development environment. You may have heard of this before. Watchdogs are memory mapped too. So watchdogs, they can be included in the microcontroller, in which case they would be a memory mapped peripheral, or they might just be like included in the microcontroller in a way that's like kind of more obscure. For the TMS 570, we actually have an external watchdog. So it's a device outside the microcontroller, and then we use a GPIO pin to pet the watchdog. So in that case, it's not memory mapped because it's outside of the microcontroller. Would there be a scenario where the watchdog would be continuously reset while in an infinite loop? So do you mean the watchdog is continually resetting the CPU in an infinite loop? Oh, so like continually petting the watchdog in an infinite loop. So the way this is usually structured is this watchdog task is periodic. So it's configured to run every, say, second, or maybe it's a much longer period, like every 60 seconds. Then so it'll only pet the watchdog every 60 seconds. And if it doesn't get pet by one of these, then it won't pet the watchdog, and the hardware watchdog will reset the CPU. So since this task is just configured to be periodic, it's not going to like repeatedly pet the watchdog. Yes, the watchdog jumpers. So the watchdog can be really annoying if you actually want your code to be paused or be hanging. So when you're debugging, you will sometimes pause the CPU to go inspect some variables or whatnot. And What that means is it won't be able to pet the watchdog. And so the watchdog will expire and reset while you're in the middle of debugging. So what those jumpers are is you can disconnect the jumper and it just turns off power to this. And so that way it can't reset the CPU. So if you're debugging something, you generally will probably want the watchdog disconnected so that it doesn't reset in the middle of your debugging session. It's a good question. Thanks, Rodrigo. And yeah, like Julian mentioned, the watchdog is it's a free RTOS task. And so we'll get into lots more about that in Mitchell's session on free RTOS towards the end of the day. Yeah, so on the OBCs, we spent a long time trying to figure out why the CPU was resetting when it wasn't supposed to be. And it ended up being the watchdogs were biting when we weren't expecting them to, tied to the fact that we were pausing the CPU. So that's why for V2, we've added these jumpers to disable the watchdogs when we don't want them to be interrupting us. But yeah, unfortunately on the OBC V1s, we had to manually disable the watchdogs and kind of permanently. Okay, let's jump into development tools. Okay, so integrated development environments. So this is the program often provided by the manufacturer of the microcontroller that makes it easier to write code and upload it to the microcontroller. So for example, the Arduino IDE, if you've used that for programming Arduinos, for the TMS 570, it's Code Composer Studio, which we'll be using for the labs today. For Silicon Labs chips, they have a program called Simplicity Studio. Again, I just threw that in there because I happened to be using a Silicon Lab chip the other day. And Espressif, they have some plugins for Eclipse or VS Code. So often the way these manufacturers do this, and actually very frequently it's based on Eclipse. So Eclipse is I think it's an open source IDE that's just very configurable. And so these chip manufacturers will go create a plugin or a customization of Eclipse for their chip. And so that's what CCS is. It's a customization of Eclipse. And actually so is Simplicity Studio. So yeah, so if you've used Eclipse before, it's commonly used for Java development, although I think it's a little less popular these days because there's like JetBrains and VS Code. But if you've used Eclipse before, then CCS will be very familiar to you, as will lots of these embedded IDEs. So using an IDE is not strictly required, but it will generally make your life a lot easier. You can edit your code in one place and use the IDE just for flashing and uploading. That's actually what I do. I edit my code in VS Code just because it's a really nice text editor. And then I use CCS just to flash and upload. But yeah, it's entirely up to you. It can make it more complicated to do it that way, but maybe the benefits of your favorite editor outweigh that. The thing you do need is the tool chain. So usually these IDEs come with the tool chain included. And the tool chain is basically just a set of programs that compile your code. Julian will talk about what specifically happens, what parts of the tool chain are used to compile the code in his compiler session a little later. But the gist of it is there's the compiler, the linker, some tools to inspect the resulting binary are often included in the tool chain, flashing tools, debugging tools, all of that. And so each chip manufacturer will have a tool chain for their chip. So the TMS 570 it has an ARM CPU, so that's why all of these are prefixed with ARM. So this is the TI customized ARM toolchain. It's just this set of programs. So that usually comes with your IDE. So next topic is JTAG. So JTAG is formally a standard describing a particular architecture for testing integrated circuits. Practically, it's a way to flash and debug code to a microcontroller. The key elements of JTAG are what's called the test access port. So this is 4 or 5 external pins. So it's this TMS, TCK, TDI, and TDO pin. And there can also be a reset pin, but that's optional. And so you might remember that those 4 pins, actually all 5, are on the test header on the OBC. So this is the JTAG test access port for, these are connected to the JTAG test access port on the TMS 570. And then inside the actual chip, there's this tap controller, which is just a state machine that controls how data comes in and out of the test access port, the tap. Oops, sorry. And then the other element is what's called a boundary scan implementation. And it's basically just a way for the chip to manually set signal levels on each of the pins of the chip. And so it's called a boundary scan because the pins go around the outside of the chip. So it's a way to set voltage levels and read voltage levels on all the pins around the outside of the chip. And so for a microcontroller, it also lets you set levels internal to the chip, because inside the microcontroller, there's a couple elements. And so you can basically control all the internal signals of the chip through this. And this is what lets us debug and flash code. So the way this looks is you have a JTAG controller connected to the tap. And this JTAG controller is typically a J-Link, one of these guys. And so if you're using our OBC hardware, we'll give you one of these to be able to create this setup. And so this JTAG controller basically knows how to use these pins to upload code to the CPU and to debug it. So just tell the CPU to halt, read registers, etc. And then you connect the JTAG controller to your computer, and there's like a device driver on your computer that knows how to talk to the controller. So for this, this cable here is what connects to your actual OBC hardware, and then this USB connection to your computer. So that's how we debug embedded hardware, kind of at the lowest level. There are some easier ways to debug embedded hardware, which you've probably encountered if you used Arduinos, because you almost definitely didn't use a JTAG or a J-Link when you were using an Arduino. And the way that works is a lot of these embedded devices, they have a UART interface, which is just like two pins, a transmit and a receive pin. And so you can just send data on those pins. And what happens often is the microcontroller has a bootloader that knows how to receive firmware images over UART, and that enables you to flash over UART. So this is what we talked about before when we were looking at the flash partitions. So this is how you could flash an Arduino without having a J-Link. And so to make it even easier, these embedded systems often also have a UART to USB bridge. And so that lets you use a USB connection instead of directly connecting the UART to your computer. So this is kind of the typical debugging setup, and this is exactly what it is on the Eliasat OBC. So to upload firmware at the kind of low level, you go through the J-Link to this test header, and then that connects to the JTAG tap on the microcontroller, and that lets you upload firmware at the low level. And then there's also the UART, which goes to a USB to UART bridge, which just converts it to USB. And then you can connect USB to your computer. And so here you can have like debug messages coming out, or if you've got a bootloader, which is in progress, you can upload firmware through here as well. The one thing you can't do through here in general is actual debugging. So if you want to like halt the CPU or set breakpoints, you have to go through the J-Link to the JTAG tap. Okay, so I think, yeah, that's the end. So are there any questions about the debugging setup, the dev tools, or anything else from the presentation?